Good morning, everyone. Thank you for the very kind introduction. So the goal of our work is to predict PBA timing using GBA features by applying machine learning. Then we integrate our model predictions into a post-route optimization flow to demonstrate non-trivial power, performance, and area PPA benefits at advanced technology nodes. So what is the advantage of using PBA? This particular cartoon over here shows the path under consideration highlighted in blue. At the merge nodes, which are U1Z, U2ZN, and U3ZN, GBA static timing analysis will always propagate the worst input slew. However, path-based optimization, or PBA, propagates the actual slew on the path. So therefore, 80 picoseconds gets propagated at U1Z, 78 picosecond gets propagated at U2ZN, and 70 picosecond gets propagated at U3ZN. And finally, we observe 61 picoseconds at the endpoint FF2D. GBST would have estimated this 61 picoseconds as a much larger number, so there is inherent pessimism. Our key contributions are as follows. We are the first to develop an application of ML paradigm to optimize post-routed designs using predicted PBA slack using a ML augmented GBA flow. We propose on-the-fly training methodology and insights on choice of features and modeling algorithms for our task. We apply several novel engineering strategies on model guidance for delay area and power recovery to reduce GBA flow over design. We integrate our methodology in a commercial EDA tool and present non-trivial PPA gains on real industrial designs across 5 nanometer to 16 nanometer. Our results show that we have a runtime overhead of about 3% versus GBA flow and up to 11.7% savings in leakage power and 1.16% savings in total power. Note that 1.16% savings in total power is a pretty significant number when we consider baseline GBA flows that are running state-of-the-art power recovery algorithms on industrial designs. And in such designs, every 1 milliwatt and 1% of total power recovery matters. This slide shows our ML-guided post-route optimization flow. On the left-hand side, we see the baseline GBA flow where we take a routed netlist, we perform concurrent clock and data path fixing of setup and hold and other electrical rules, and thereby we apply area and power recovery again on the clock and data path, followed by legalization and ECO route. On the right-hand side, we augment our ML methodology to this baseline GBA flow, wherein we create two models. One of these models is trained during delay fixing, and the model predictions are incrementally applied during delay fixing. And the second model is trained during area and power recovery and incrementally applied during area and power recovery optimization steps. The reason in this figure we show two models is because there's a huge shift in PBA labels, which doesn't make the delay model generalized to the recovery model. Here we show the accuracy of our ML model as measured by the ratio of the root mean squared error with the default, that is GBA minus true PBA, and the root mean square of the predicted PBA minus true PBA. As we see, we can gain up to 30x improvement in root mean squared error. Here we show results of PPA. First, we normalize total negative slack to path delay for unbiased comparisons. As expected, ML augmented GBA flow improves area and power, so we get up to 1% area, about 1% power and total power, and 11.7% leakage power. The gamma shows leakage only designs. Now, on certain designs, we have TNS losses, and these are mainly due to two reasons. Inaccuracy is due to model reuse, and model limitation as PBA path is used for training. That was a presentation, and thank you for listening. I'd be happy to take any questions.